Hello, welcome to part 2 of session 7. So we continue with our discussion of the normal distribution. But in this session, we will teach you how to compute percentile points for normally distributed variables, and also how we can use the normal distribution to approximate the binomial distribution and then the Poisson distribution. As usual, our texts are Michael Barrow and Mason, Lind, and Marshall. So at the end of this session, when you finish reading, you can go back to the text and read the relevant chapters. Okay, so percentile points for normally distributed variables. You recall that we earlier on discussed percentiles. Okay, so and we said that when we talk about, let's say, the 90th percentile, we're looking for a value x such that 90% of observations are below this value and 10% above it. But in the case of the normal distribution, especially the standard normal, the 90th percentile will simply be the z value such that the area under the normal curve to the left of this z value is equal to 0.9000 or 0.9. And the area to the right is 0.1. Since the total area is 1, summing 0.9 and 0.1, you get 1. So we're saying that the total area under the curve is 1. And if you look, you want in the 90th percentile, then you want to mark a point where the z value that we'll get will be such that the total area to the left of this z value is 0.9 and the area to the right is 0.1. So once you know the percentile you are interested in, all we do is to use this formula. So if you want to determine the value of a percentile point for any normally distributed variable, for example x, other than the standard normal, all you need to do is to find the z value that corresponds to that percentile. Once you find the z value, then you can convert to the corresponding x by solving for x in this formula. So if z is equal to x minus mu over sigma, we can solve for x and it gives us x must be equal to mu plus z times sigma. It's as simple and straightforward as that. So let's use the question that we solved in the first part about the equipment repair time. Okay, you recall that we said the mean equipment repair time was 50 minutes and the standard deviation was 10 minutes. So let's say that we want the equipment repair time at the 90th percentile. What it means is that we want to find the z value such that the area under the standard normal curve to the left of z is 0.9. Now, but recall that we are dealing with the half table, right? So if we are dealing with a half table and we want the area to the left to be 0.9, it means that the area to the left of the mean of 0 will be 0.5, and therefore between the mean of 0 and where our z must be, the area should be what? 0.4. So we're saying that given the standard normal table we are using, where the reading starts from the mean of 0, we must find the z value corresponding to 0.4, since the left half of the curve is 0.5. So if you add your 0.4 to the 0.5, you still get your 0.9, right? So how do we get the z value corresponding to an area of 0.4? Now, it means that we read the normal table in the reverse order. First, what we're doing was that we know the z value, okay, and we find the area. But now we know the area, we want to find the z value. So you read the table in the reverse order, okay? You read the table in the reverse order. So it means that you take the normal table and look in the body of the table, okay, and you look for the area in the table closest to the value 0.4000. If you look in the table, the area closest to 0.4000 is 0.3997. And the z value that corresponds to it is 1.28. The z value that corresponds to it is 1.28. So then we know our z is 1.28. So given that our mu is 50, our sigma is 10, then to calculate the equipment repair time at the 90th percentile, it's a matter of substituting these values into this formula. Because we know our mu is 50, our z is 1.28, our sigma is 10. So 50 plus 1.28 times 10, it gives us 62.8 minutes. Now, how do we interpret this? It means that 90% of the equipment will require 62.8 minutes or less to repair, while 10% will require more than 62.8 minutes. It's as simple as that. Now remember that for percentiles that are less than 50, you can also determine the z value that corresponds to it. But the z value will be negative because you are in the negative half of the curve. Okay? So for example, if you want to find the 20th percentile, what will it be? Okay, don't go to the next slide. Try and calculate it yourself, but you see the answer on the next slide. And this is what it gives you. It gives you 41.6 minutes, right? And the explanation why it is so has been given. Now, the next topic is to talk about the normal approximation of the binomial. Now, we can use the normal distribution to approximate the binomial. In other words, you have a problem that seemingly is a binomial situation, but you don't use the binomial formula that we discussed earlier to solve it, but rather you use the normal. And we are saying that the conditions under which you can do that is when the sample size is large, maybe greater than 30. Now, in other words, when the number of times the experiment is conducted is large, and then the product of the sample size and the probability of success P is greater than 5, then we can approximate the binomial with the normal. But when you are dealing with the normal, you need two key variables, the mean and then the standard deviation. But you can find the mean simply as what? NP. Recall that we said the mean of the binomial was what? NP, right? So the mean. And then you can find the standard deviation as the square root of NP times 1 minus P. Once you found this, you can apply the formula for calculating normal probabilities to determine the required probability. Now, recall that when you approximate the binomial with a normal, you would have to do what is called correction for continuity, okay? Because you see, suppose we wish to determine the probability of obtaining 20 heads in 30 tosses of a coin. We know we can actually solve the problem using binomial, right? Because that's a binomial. Heads or tails, success and failure. So since our success is heads, the probability of a head P is 0.5. We know that. So we want to find the probability of the heads being greater than or equal to 20, given that the coin is tossed 30 times and the probability of head is 0.5. When you use the formula as we've illustrated earlier in binomial distribution, you will get the answer 0.0494, right? But if we want to solve this problem using the normal, then we need to find the mean which is NP, and it must be 30 times 0.5. So the mu now is 15, and our standard deviation using the formula gives us 2.74. So we want to calculate the probability of x greater than or equal to 20. But it means you are approximating a discrete distribution with a continuous distribution. And we need to treat it as if we are on a continuous scale. Now, how would you interpret 20 or more in a discrete situation in a continuous sense. Now, because it is continuous, you have to interpret 20 or more as if 20 is inclusive. But where is the lower boundary? Where does 20 start from? 20 must start from 19.5, because that's the boundary that separates 20 and 19, right? Because it is continuous, it's not discrete. We don't want gaps between them. So to calculate the normal probability, you have to subtract 0.5 from 20. You subtract 0.5 from 20, which gives you 19.5. So the probability that x is greater than or equal to 20 for the binomial must be equal to the probability of x is greater than or equal to 19.5 for the normal. And when you calculate it, you get 0.0505. It means the answers are very close. The first one was 0.49, which is 0.049, which is the same as 0.5, right? 0.05. And this is also 0.05. So it's approximately fairly well. So in general, this is how you do your correction for continuity. If in the binomial, you were solving the probability of x being less than a certain value, then what you should do is to subtract 0.5, because the value b, since it is not included, right? And then when you say probability of greater than, you add 0.5, because the point A is exclusive. Probability of x less than equal to b, you have to add 0.5. But if it says probability of x is greater than or equal to a, you subtract 0.5, as we just did. So this is how you deal with the correction for continuity. The next is to also look at how we can approximate the Poisson using the normal distribution. Now, what is the condition? When the mean of the Poisson distribution is large, where we are assuming that it is greater than or equal to 10, then the normal can be used to approximate the Poisson. And we need the mean for the normal, and the mean is just equal to the mean of the Poisson. So your mu is the same as the lambda from the Poisson. And then we find our sigma to be equal to the square root of the lambda. Now, the correction for continuity that we just talked about also applies here, because again, the Poisson is discrete, but the normal is continuous, and we are using the continuous to approximate the discrete. So we need to correct for continuity. So let's say this question says that an average of 10 calls per day come through a telephone switchboard. What is the probability that 15 or more calls will come through on a randomly selected day? So we want, this is a Poisson, so we want a probability that x is greater than or equal to 15, given that the mean is 10. When you solve this using the Poisson, you get 0.0835. But we can solve this using the normal. Okay, so we correct. So our mu, which is lambda, is 10, and our sigma, which is square root of lambda, is 3.16. So the Poisson probability can be approximated by the normal probability. Since we are saying that greater than or equal to 15 means 15 is inclusive, so we must subtract 0.5 from 15. So it is probability of x is greater than or equal to 14.5. And when you calculate that, you get 0.0778, which is also close, the same or approximate. Okay, it's 0.08 in both cases. So this is how you can use the Poisson to approximate, the normal to approximate the normal to approximate the Poisson as well. Now, as you know, there will be problems in your for each session that you would have to practice. So with these few examples that I've solved, I would expect that you practice those problem sets that I'll put up for you, so that you can perfect, because it's always said that practice makes perfect. This is the end of the part 2 of session 7. We'll move to session 8 right away. Thank you very much.